Lesson 18 is dilations of polynomial functions. So we've done translations, and that's where you shift a function left or right or up or down. Dilation is when we change kind of like the shape of the function by multiplying in a scale factor. So before we get into the actual notes, we're going to go through another Desmos exploration. So click on the link in the printable version if you want to kind of go to your own Desmos. If not, you can just follow along on here, and then you can continue without signing in. And then just put in like your first name, your initials, or anything you want, and then you can press go to move forward. Okay, so notice there's two functions. One is f of x equals a times 1 over b x squared, and then the second one is almost the same thing, has the same a and 1 over b, but it's cubed instead of squared, so that's our cubic function parent function, or cubic parent function. And then the other thing I want to point out before we get started is we can see a and b are like kind of our variables here for the dilations, and their starting values are 1 instead of 0. So with translations, they were 0 because like we were moving, if there was no transformation, we'd be moving like 0 units left, right, up, or down. In this case, if our transformation is a dilation or like multiplying in a scale factor, so multiplying by 1 would be like the no transformation version because multiplying by 1 isn't changing anything. So they're starting at 1, that's kind of like the default. And then a is the like variable that we use to represent a vertical not translation, but a vertical stretch or a vertical dilation. So vertical means that it's like pulling the graph in a vertical way. So like, for example, if I have a vertical stretch or a vertical dilation and I increase my value of a using the slider, you can see that the graph like pulls vertically up and away from the x-axis. Versus if I make it smaller, it's getting It's getting compressed vertically. It's getting like smushed down towards the x-axis. And then if you notice, like if I make it 0, then it's no longer a quadratic. So that's why like kind of the default is 1. Because if a is 0, it completely eliminates the x squared term because you'd be multiplying it by 0 and it would go away. And then you'll notice like if I make a negative, the graph actually flips like upside down beneath the x-axis. So that would also be a reflection. So with that a value, we can do a vertical stretch and also reflection over the x-axis. Notice that, so if the parent function, kind of like the starting amount, is like a equals 1, when we're between 0 and 1, so like 0.7, it's getting like vertically compressed down towards the x-axis. You'll see the word compression. You'll also see the word shrink. Those mean the same thing. It's just what happens when there's a dilation without a scale factor that's between 0 and 1. And that's also like kind of including the negative values. So we typically say it in terms of absolute value. So like right down here, the graph was still kind of like compressed, like it's more smushed than the original like parent function. The a value is negative 0.4, so it'd be like a shrink of 0.4 and a reflection because the negative part is flipping it upside down. If I keep going and I make a even more negative, like in this case negative 2.7, the graph is stretched down away from the x-axis, so it'd be like a stretch and a reflection. Okay, all this stuff we're gonna like talk about more formally within the like regular note section, but it's just kind of like a way of playing around and seeing like how the graph kind of moves in real time. And then the variable for b is a horizontal stretch. So a was vertical stretch, b is horizontal stretch. So you'll notice like in the function itself, there's a 1 over b. So like, for example, if I stretch the graph horizontally by a factor of 2, I would change b to 2, and you could see it stretching it horizontally. Like, I'm going to make it actually a little bit bigger than 2. So it started at b equals 1, and then as it gets bigger, the graph is stretching horizontally away from the y-axis in this case. But if I were to take that 3.5 and put it in my function, it would actually be 1 over 3.5. So we always put the reciprocal of b like in our function itself. It's just kind of like one of those little funky things we got to remember. But like I said, we'll play around with it more in the formal notes. And then there can also be a like vertical reflection or reflection over the, not vertical reflection, flexion, horizontal reflection or reflection over the y-axis, but it's kind of hard to tell with this graph. So you can see like as b gets smaller, it's shrinking horizontally, and then when it becomes negative, it just kind of like reflects over itself because it's reflecting over the y, so it just becomes kind of the same function. It's a little bit easier to see that one with the cubic. So I'm going to take the quadratic off and we'll focus on the cubic. So the second line, f of x equals a times 1 over b x cubed. So same concept here, like for a, that's my vertical stretch. So, or compression, depending on what the value of a is. So if I make a bigger, it's stretching the graph up and away from the x-axis. I know it like looks like it's just getting like pushed towards the y-axis, but think of it as like the two tail ends like getting pulled and like becoming more like taut is kind of how I picture it, which is just like, you know, a rope that's getting pulled tighter. And then if there's a vertical compression, that's like when there's an a value that's less than 1, you can see it's like kind of getting smushed a little bit vertically. And then as a becomes negative, the graph flips upside down. So this is when a is positive. When a is negative, it flips upside down. And then for b, that's our like horizontal stretch or shrink or stretch or compression. So if I make b greater than 1, it's going to stretch it horizontally. It should pull it away from the y-axis, which it does. And then if I make b less than 1, greater than 0, it's going to shrink it horizontally, so it's going to like push it closer to the y-axis. And then if I make b negative, you should see it reflect over the y-axis. So instead of like it being in the first quadrant and the third quadrant, it should be in the second and the fourth. So we'll make b negative and it flips over like that. Okay, so we'll go back to the regular note section. We're going to write just like a few functions with these transformations. So starting with vertical dilation, which the formula for vertical dilation is a times f of x. So we're multiplying a constant through like whatever our original function is. So for number 1, it says f of x equals 2x minus 3 is vertically compressed by a factor of 1/3 to get f prime of x. Write a rule for f prime of x. So if we're writing a rule, we don't really need to necessarily worry about like how it says compression. So whether it's like compressed or stretched has to do with what the factor is. So if it's a vertical, we're using the a as our factor. So we would say like the absolute value of a, if that's greater than 1, it's a stretch. If the absolute value of a is less than 1 but greater than 0, it's compressed, or it's a shrink, but compress and shrink are the same thing. We use the absolute value here because if it's negative, then like it would just be a reflection. But like for example, if I didn't use the negative or the absolute value, if I said a was -2, that's technically less than 1, but it wouldn't be a compression. It would be a reflection with a stretch. Okay, so now I'm going to kind of take this 1/3 and put it into this little formula that we have for vertical dilation. So that just means that 1/3 is going to be my a value. So if I rewrite the formula with my actual a, 1/3, that's a scale factor. It'd be 1/3 times f of x. And that's going to give us f prime of x. Okay, so instead of a times f of x, the scale factor that we're compressing by vertically is 1/3, so it'll be 1/3 times f of x. And then now I just need to take what f of x is and put that in the function. Since there's multiple terms, I need to use parentheses here to make sure that I actually multiply like the whole function by 1/3. So it'd be 1/3. And then if I just put like times 2x minus 3, I'm not going to multiply the entire function by 1/3, and I have to in order to make sure I'm compressing the entire thing. So I'd use parentheses. And then I would just go ahead and distribute the 1/3 in. So we would do f prime of x is equal to 1/3 times 2x, so that would be 2/3 x. And then 1/3 times -3, so -1. So f prime of x is equal to 2/3 x minus 1. Okay, and then number 2, so f of x equals x squared times x minus 3 squared plus 3. Red rule for f prime of x based on the dilation in the graph. So we're given the green function f of x, and we want to write the kind of reddish function f prime of x. But we have to figure out what transformation is happening in there. So to do that, we look at the 2 points that were given. So 3, 3, and then 3, 9. 3, 3 is becoming 3, 9. So a vertical translation is when the y value is changing, because if it's stretching something vertically, it's pulling the y value up or down by a scale factor. Scale factor means multiply. So we think, okay, what am I multiplying by to get from 3 to 9? I'm multiplying by 3. So that would mean that my A, so vertical stretch means look at the y. And then horizontal, we would look at the x, because that's changing the width of the point. Okay, so as soon as we know that a equals 3, instead of a times f of x for my vertical stretch or shrink, it would be 3 times f of x. In this case, it's a stretch because a is greater than 1. And then I just have to actually take my big long function now and put it in for f of x, and then since it's that whole thing, I'll have to use parentheses. So it'd be 3, and then parentheses, f of x was x squared. I'm going to change this to brackets actually, since we already kind of have some parentheses. So x squared, and then times x minus 3 squared plus 3, and then brackets around the end. And then the new function we're supposed to call f prime of x. And then we do need to distribute this 3 in. We'll distribute it to the x squared. We don't distribute it to the x minus 3. Think of those parentheses as kind of like jail cells, so nothing goes in, nothing comes out. And then we just need to make sure that we distribute that 3 to the 3 at the very end. So f prime of x is equal to 3 times x squared, so 3x squared. The parentheses part stays the same, so times x minus 3 squared, and then 3 times 3 at the end, so plus 9. Okay, and then one more time with the parentheses. It's just so this x squared is already being multiplied by the x minus 3 squared, so if I put the 3 inside the parentheses as well, it's kind of like multiplying it twice, but it's just being multiplied by that entire term. Okay, so f prime of x equals 3x squared times x minus 3 squared plus 9. And then we'll move on to number 3 on the right side of the page. We're going on to horizontal stretch and shrink. So horizontal dilation is f of 1/2. Sorry, no, I keep saying, in my mind I see the fraction, I think 1/2. I don't know why, but f of 1/bx. So same thing here, if b itself, if the absolute value of b is greater than 1, it's a stretch. And then if the absolute value of b is less than 1 and greater than 0, it'd be compress or shrink. So for number 3, f of x equals x cubed minus 3 is horizontally stretched by a factor of 2 to get g of x. So again, we don't really it's nice to know that it's stretched, but really the factor of 2 is automatically a stretch. We don't have to do anything funky for the stretch. We just have to make sure that we're doing it horizontally. So if it's horizontally, it would be using this formula versus the first formula we use would be for vertical. Okay, so if we rewrite our formula f of 1/bx with that actual stretch factor in there, b would be 2. So this would be f of 1/2 x. So what this means is it's kind of like when we had the horizontal translation if we change something that's in the parentheses, that means that we have to like change all of the x's that are inside the function. So our function would be, new function is supposed to be called g of x. Oops, not g prime. But g of x is equal to, if I have a 1/2 x inside the parentheses, that means I have to change my like regular x to a 1/2 x. So 1/2 x, and then in parentheses to the third power minus 3. So I kind of want to go through that one more time. I'm going to write this like f of 1/2 x right above a little bit. It might help a little bit. Okay, so if we're supposed to do like a horizontal stretch, b is 2, so it'd be f of 1/2 over x. So you could see like in the original function it's f of x, and we're changing it to f of 1/2 x. And then that means that instead of x in our function, we're going to replace it with that 1/2 x, and that's what we did right here. So instead of it being like x to the third power, the x got swapped out for the 1/2 x. And then the rest of the function stayed the same, so minus 3 at the end and minus 3 at the end. Okay, I'm going to try to erase that clutter. Big thing is just to remember that like if you make changes to the inside of the function, like we do for horizontal translations or horizontal dilations, those changes replace the original x's in the function. And then this part we can go ahead and simplify, like 1/2 x cubed. That means 1/2 cubed and x cubed. So we can just go ahead and cube the 1/2. So 1/2 cubed means like 1/2 times 1/2 times 1/2. So that'd be 1/8 altogether. You just cube the numerator and denominator. So 1 cubed is 1 and 2 cubed is 8. So g of x equals 1/8 x to the third power. And then now like the power just belongs to the x, so that's why we take off the parentheses, and then we bring down the minus 3. So g of x equals 1/8 x cubed. And then for number 4, so we're starting with the same function as we did for number 2. The like kind of way that the graph is scaled is a little bit different, but it's the same function. So f of x equals x squared times x minus 3 squared plus 3. Write a rule for f prime of x based on the dilation in the graph. So we're given the green function. We want to write a rule for the kind of magenta function. So in order to do this, we have to look at the 2 points that were given. So 3, 3, and 6, 3. And then in this case, if we look at the y value, like the y value is not changing. The x value is what is changing. So if the x value is what is changing, that's a horizontal dilation. So for horizontal dilations, we would look at the x coordinate, or like if you see that the x coordinate is what's changing, then it's a horizontal dilation. If you see it's the y coordinate that's changing, then it's a vertical dilation. Think about like, I guess the easiest way to remember is like your x coordinate is like what's controlling the width of the graph. So if the x coordinate is changing, then it's changing horizontally. The y coordinate controls like the height of the graph. So if the y coordinate is changing, then like it's changing vertically. Okay, so we're looking at like the x coordinates here. Those are what's changing, and since it's a dilation, it's a stretch. We're talking in terms of like a scale factor. A scale factor is a multiplied number. So we would think, okay, what am I multiplying 3 by to get to 6? I'm multiplying by 2. If this were ever the case where like, say we were going from 6 to 3, we wouldn't think of it in terms of dividing. We would still think of it in terms of multiplying. It would just be like multiplying by half. So if it looks like you're dividing by a number, think multiplying by the reciprocal of that number. So like in the case of number 2, like if I was going from 9 back to 3, like if the red one was my original function and the green one was the one I was going to, then my scale factor would be 1/3. Okay, so we're multiplying by 2, so that means that b is 2. So if I rewrite the function, I just realized it's the same scale factor, oops. But my like little formula would be f of 1 over 2, because it's supposed to be 1 over b x. And then now I just need to actually incorporate that into my original function. So for this one, I'm going to rewrite the original function really quick, just because it is like a little bit more complex. So it's f of x equals x squared parentheses x minus 3 squared and then plus 3. And then if I'm changing it to f1/2 of x, that means that wherever I have like an x in my function originally, it's going to get replaced with this 1/2 x. So this would become a 1/2 x squared. And it needs to go in parentheses because originally like this entire x was being squared, so now this entire thing needs to be squared. And then for the second parentheses, I would replace the x with 1/2 x. I don't need to use parentheses around that 1/2 x specifically because this part, this x was not being squared or anything. It was just like the whole quantity, the minus 3, those being squared. And then I can't forget that plus 3 at the end. And then now I just need to simplify like a little bit. So I'm going to backtrack a little bit just to kind of show how we ended up from that first line to that second line. So the original function was f of x. So we had like our input was x. So there's an x right here and an x right here. And then our input was changing to 1/2 x. So instead of that first x, it became 1/2 x squared. The second one became the 1/2 x there. So we replaced all of the x's with 1/2 x. And then now we just need to simplify. So the only thing we really can simplify is this part. We're not going to FOIL this. We're just going to leave that as is. So for the 1/2 x squared, like, or 1/2 x in parentheses squared, I need to just square both. So my final function is supposed to be called f prime of x. And then if I square this entire quantity, if I square the 1/2, I would just square the numerator and denominator, so it'd become 1/4, like 1 squared and 2 squared, and then x squared. I just don't need the parentheses anymore because I've already squared the 1/2. And then the rest of the function just comes down. So parentheses 1/2 x minus 3 squared and then plus 3. So f prime of x equals 1/4 x squared times 1/2 x minus 3 squared plus 3. Okay, the next two problems are dealing with reflections, and then we have one kind of like combo problem at the end. So for the lower left corner, the reflections over the x-axis. So reflections over the x-axis means that you'd like negate the entire function, so you're making like all of your original output values negative. Output values are the y's. So think if I have my y values and like picture in your head they're all positive, and I make them all negative, they're going to flip down below the x-axis. So that's how we create the x-axis reflection. And then the y-axis, we're negating the input. The input is the x values. So picture if I have like a bunch of positive x values and I make them negative, they're going to flip over the y-axis. So that would be f of negative x to reflect, to reflect over the y. So for number 5, f of x equals x plus 5 times x plus 1 times x plus 2 plus 3 is reflected over the x-axis to get g of x, root over for g of x. So if it's reflected over the x-axis, we just need to know that we need to multiply the entire function by a negative. So that means that I'm going to use the negative f of x formula, and then it's just going to be a negative, and then all of what was originally f of x. I do have to put it in parentheses because of that like plus 3 at the end kind of incorporates like a second term. So negative, and then I'm going to use brackets, x plus 5 times x plus 1 times x plus 2, and then plus 3. And then now I just need to distribute that negative in and then call my final function g of x. So g of x equals, so when I distribute the negative to like the first part, this whole thing is just like one massive term because they're all being like multiplied together. So I just have to slap a negative in front of that whole thing. So negative x plus 5 in parentheses, x plus 1 in parentheses, times x plus 2 in parentheses, and then that part's taken care of. And then I just need to make sure that I distribute the negative to the 3 at the end, since that was like outside of the like kind of group of parentheses. So that plus 3 becomes a minus 3. And then that's my final answer. So g of x equals negative x plus 5 times x plus 1 times x plus 2 minus 3. And then if that x minus or x plus 3 in the original problem wasn't there, it really would have just been good enough to put a negative in the very front of the parentheses. You don't have to distribute it into the parentheses. And then 6, so same exact function, f of x equals x plus 5 times x plus 1 times x plus 2 plus 3 is reflected over the y-axis this time. So if it's reflected over the y-axis, you need to know that like this is the formula that you use, f of x minus x. It means that you need to negate the input. The new function we're supposed to write is f prime of x. Sorry. So I was getting ahead of myself. I'm gonna backtrack and use this formula. So f of negative x. So for number 6, the negative out in front meant that we multiplied a negative like throughout the entire function. The negative inside of the parentheses means that we have to switch out all of our x's for negative x's. So same thing as like horizontal translations and horizontal dilations. If you're making a change to the inside of the parentheses, then you have to make a change to every single x in the function. They all get switched out for negative x in this case. So f of negative x would be negative x plus 5 times negative x plus 1 times negative x plus 2 and then plus 3 at the end. We don't need to make any changes to that because it doesn't have an x. All we have to do is everywhere there was an x in the original function, it's getting switched out for negative x because we're changing from f of x to f of negative x. Okay, and then there's really no simplifying we have to do here with the like negative x plus 5, negative x plus 1, negative x plus 2 plus 3. So I'm just going to go ahead and erase the f of negative x and change it to my f prime of x, just to save us a little bit of writing. So f prime of x equals negative x plus 5, negative x times negative x plus 1 times negative x plus 2, and then plus 3 outside the parentheses. Okay, so comparing the two types of reflections, if you have a reflection over the x-axis, and it'll tell you, or you'll see it in the problem itself, like on a graph. If you have a reflection over the x-axis, you multiply the entire function by a negative. If you have a reflection over the y-axis, you swap out all of the x's for negative x's. Okay, so last problem, f of x equals x plus 1 squared times x plus 3 minus 1. Write a rule for g of x based on the transformations in the graph. So we want to look at what different things are happening in the graph. So in order to do that, first things first, like we can see that the graph is reflected. Like one is facing one way, one is facing the other way. So we're starting with the green function, we're going to the red function. So we can see there's like a reflection over the y-axis. I'm just going to make a note of that because like this is kind of, reflecting is the best word to describe it. It's like flipping over the y-axis to get the new one. And then, of course, like the points are shifting as well. There's some sort of like stretch or shrink or something. We'll talk about that in a second. So first, there's a reflection over the y-axis. And then a reflection over the y-axis, the formula for that is f of negative x. That was like the last problem we did. So reflection over the y-axis is f of negative x. And then to figure out what the dilation is, you want to pick a point that's like kind of a key point on each function. So what I mean by that is like we can see the one that pops out to me at least, and they do give you one in the workbook, but I think it's helpful to like be able to identify one on your own as well. So the one that pops out to me is like this 0.02 or negative 2, 0. It flips over, so it would have been like over here, but then it shrinks down like to right here. And the way that you can tell is like, so the graph is dipping down here like below the x-axis, and then when it first comes up above, it gets to this point. Whereas on the reflected one, it's like first dips down below the x-axis, and then when it first comes back up to the x-axis, it's at this point. So those points are like corresponding, for lack of a better term, so we can use them to figure out what sort of like dilation there is. So this point It's negative 2, 0. This point is 1, 0. So we already talked about how there's a reflection in the y-axis, which that negates the input, which means it makes the x-axis or the x-coordinate of the point switch signs. So our x-coordinate from these points switched from a negative to a positive, but what happened like with the value of the number? So it went from a 2 to a 1, or well, negative 2 to 1. So we have to think, okay, how did I get from 2 to 1? I would have to multiply by a half. So we don't think in terms of dividing, we think in terms of multiplying always. So even though I'm dividing by 2, to get from 2 to 1, that's the same thing as multiplying by half. And then I'm going from a negative to a positive, so it'd be negative 1/2. I'm not going to worry about that necessarily right now, though. We'll just list the horizontal shrink. So there's a horizontal shrink or compress, and the factor is 1/2. Okay, so our formula for a horizontal dilation is f of 1 over bx, and b is like the factor that it's being compressed by, so ours is being compressed by a half. So b would be a 1/2, but 1/2 isn't the thing that we put in here, like it wouldn't become 1/2 x. B is 1/2, so we'd have to put 1/2 in there and then simplify. So I'm just gonna kind of do it off the side really quick. So it'd be 1, not off to the side, but like not within the like f of x part. So it'd be 1 over b, and b is 1/2. So usually, like, instead of dividing by fractions and we multiply by the reciprocals, sometimes when I see like a fraction within a fraction, it looks a little bit overwhelming. So one thing that can help is to write it horizontally as a division problem, because that's what fractions are, they're dividing. So this would be the numerator 1 divided by the denominator 1/2. And then instead of dividing by a fraction, we could do multiply by the reciprocal, so it'd be 1. And then instead of divided by times the reciprocal of 1/2, so 2 over 1. So 1 over 2, or 1 times 2 over 1 is just 2. So 2 is the part that like completely replaces that, because this was 1 over b, and then 1 over b simplified to 2. So when we write like our final function here, it would be f of 2x. So horizontal dilations, like, they are pretty funky, because whatever it looks like in the function, it's the reciprocal of that on the graph. So if you see a fraction in the function, it's actually a stretch, like, and then if you see a like whole number like 2 inside the function, it's actually a shrink by the reciprocal of that, so 1 over 2. So in this case, we had the shrink of 1/2. In the function itself, it's the reciprocal of that 2. Okay, and then now we'll just go ahead and take these two kind of like function formulas and combine them into one, because this is one combined transformation. So altogether, it would be f of negative, for the reflection, 2x. And that means that wherever I have an f in my function, or an x in my function, I replace it with negative 2x. So I'm going to rewrite the function over here. So it was f of x equals x plus 1 squared times x plus 3, and then minus 1. And then my new function, I'm going to use this little kind of like formula to guide me. So it's f of negative 2x. And that means wherever I have an x originally in the function, it gets replaced with negative 2x. So this would be negative 2x instead of x, and then plus 1, parentheses squared, and then the next parentheses, negative 2x instead of x, and then plus 3, close parentheses, and then bring down the minus 1. So altogether, final function is supposed to be g of x, so it would be g of x equals, and there's no simplifying to do here, we wouldn't like FOIL it or anything like that, so negative 2x plus 1, parentheses squared, minus 2x plus 3, minus 1. So g of x equals negative 2x plus 1 squared times negative 2x plus 3 and then minus 1. Like I said, the horizontal like compressions and stretches, like those are funky because they are the opposite of what they look like. It's honestly kind of like the horizontal translations as well, because that was the one where we had to kind of flip the sign to see which direction we would be going. So give yourself patience, just know that they take a lot of practice.